And so you just get 4. Okay, now this multiplication. What's 1 over x times 1? 1 over x, right? So I have plus 1 over x. And then over, okay, here to here. What's this? What is that? It's 1, right? That's 1. And then here to here, minus 3 over x, right? Negative 3 over x or minus 3 over x. Anyone have questions there? Does anyone see why we did that? Yeah, but why? Can you see now why that was very helpful to do that? If I ask you to take the limit now, right? Now let x go to infinity. Let x go to infinity. That's just what? 4 plus, what's 1 over infinity become? 0, right? That's fixed over infinity, isn't it? Fixed number 1 over something that gets infinitely big, so that goes to 0, right? So when I take this limit, this thing right here is going to head to 0. This right here is 1, right? Minus, and then 3 over infinity. Isn't that a fixed number over infinity? What does that go to? 0, right? So what am I left with? 4 over 1. So your answer is 4, right? Some of you might remember this from college algebra. In college algebra, when you study rational functions, this right here, this function I gave us just now, is an example of a rational function. It's a polynomial divided by a polynomial. And in college algebra, you're asked to find the horizontal asymptotes, right? And different teachers teach it different ways, but there is one way where you say, okay, look, I'm going to look at the degree of the numerator and denominator. You look at these degrees, and if they're the same, your horizontal asymptote is this number divided by the number in front of that. Do y'all remember seeing that in college algebra? That's basically what we just did, but we're doing it with limits, as opposed to just doing it blindly without understanding why it is this, all right? I want that. I don't want this, all right? I don't want you just, and I'm going to give you problems on your exam. You'll have a problem where you can't do this, like it won't work. So I just don't want you trying to say, well, why, if I already know the answer is 4, why do I have to do all that limit stuff, right? All right, I want to kind of revisit this again. Why do you think, this is like a deeper question. I'm not sure who's going to understand this or not. Why do I look at the bottom when I'm doing these problems? Why do I look at the bottom and I find the highest power of x and then come through with something that will make it go away? Why?
So you can make it into a 0.
Make what into a 0? You're on the right track, but
Fixed over infinity. If infinity is just next to a number, then it'll be infinity.
I'm asking, why do I look for the highest power? Why is it that I'm going after the highest power on the bottom and trying to make it cancel out and go away? Why the bottom and why the highest power?
The highest power, because if you get rid of the highest power, all of the lower powers also go to anything over x.
Okay, pause, excellent, perfect. So think about it. If you have a denominator, no matter what's in it, if you make the highest power go away, right, you're going to have to divide by something that's going to make that go away. All the other terms have powers lower than that. So whatever you divide by, you're still going to have x's on the bottoms, because the only one that canceled was the highest power. So like, let me just write down. Let's say we had a fraction, we had x cubed plus x squared plus x. Let's say we had that down there. If I want to get rid of this, what do I have to divide it by? X cubed, right? So I'd have to get an x cubed here, x cubed here, x cubed here, right? Because I did the highest power, all of these are still going to be left with an x on the bottom, aren't they? Right? And if all of these have an x on the bottom, when I take the limit, these will all go away, won't they? You all see that? Wow, y'all got to give me some responses. I mean, I'm getting just like flat line, nothing. If you don't understand, you need to tell me. If you do, you need to let me know. But no response, then I'm just going to plow through. All right? Do you get that or not? You know how we did here? We looked at the highest power of x, x to the first power. So I came in with a 1 over x. When I distribute that through, it really just puts an x below each of those, right? That's really what happens. That's what I'm saying here. If we started with a problem where that was our denominator, and we took the highest power of x and tried to kill it off, we would come through with an x cubed underneath each one, right? This one would turn into a what? 1, right? This one would turn into a 1 over x, and this one would turn into a 1 over x squared. Got it? So because we knocked out the highest power of x, the remaining terms will all have x's in the bottom still, and then when I take the limit, they all go to 0. Guaranteed, right? That's the first observation. Why the denominator, though? Why didn't I do that for the numerator? Why did I go after the denominator and not the numerator? No. No, I mean, you're thinking, that's good. It has nothing to do with it, you can only do it to the bottom. There's a reason I went to the bottom and the bottom only. Yes?
Is it because, like, based off of the rule, the bottom is what is kind of like a tail sign of it?
It does have to do with the fact that the bottom has always been the thing that has caused issues for us in the past, right? Like imagine you did this and all of them became 0, right? What if all of these went to 0? Then what would be on the bottom? 0, and can you have that? You don't want that, right? You don't want 0 on the bottom, right? What you want on the bottom, what would be great on the bottom is a number, right? Just a number. And so that's why we go after the bottom. If we do the highest power, right? This highest power, I'm guaranteed that this is going to turn into what? 1. 1, right? And then the rest of it can go to 0 all at once. I still have a number down there. I don't have 0. Yes?
But if the bottom was 0, can you use the fixed number over 0 rule? And then it would just go to...
Well, you don't know what your numerator would go to. Just because your denominator goes to 0 doesn't mean that your numerator is going to stay fixed. Or you don't know what the numerator would do, right? Let me...
That'd be an option.
Let-
If it ended up being a fixed number and the denominator ended up being 0, then...
It won't work. Let me do that same problem we just did. 4x plus 1 over, what was it, x minus 3? So let's say, just for the sake of demonstration, that instead of doing the highest power of x down here and getting rid of it, you decided to do 1 over x squared instead, out front and top and bottom. Okay, let's just say you did that. Then this would be, all right, let's distribute through here. On the bottom, let's do the bottom first. What would that first term be? What's this times this? 1 over x. Come on, everyone. This is just algebra, right? This times this is the same as this times that. Cancel on x, right? This is 1 over x. I hate saying this is just algebra, but that, I mean, it is. That is, here to here, what do you get? 3 over x squared, right? Minus 3 over x squared. Okay, I'm doing this because I want to show you, these both go, if I take this limit, these both go where? To 0 now, right? So isn't the bottom going to be 0? And I think what you're suggesting is, well, then couldn't we use the fact that the top is fixed and then fixed over 0, right? Kind of. Well, what happens to the top, though? 4 over x plus 1 over x squared. And where does that go? If I take this limit, that goes where? Fixed over infinity? Fixed over infinity squared? 0? Now you're still bad, right? You still need algebra, you need something, right? So it doesn't help us just to arbitrarily like pick something. We always want to look at the highest power in the denominator and then kill it off. And then everything should work smoothly from there. Let's do another example, all right? All right, how about this one? How about 3x minus 5 over x squared minus 3x plus 1? Make that plus 3x on the bottom, because I haven't talked about that yet. All right, let's let x go to infinity. 3 times infinity? Infinity. Minus 5. Still huge, right? So we've got a huge number on top. And on the bottom, infinity squared. Infinity. Plus 3 times infinity. Huge, right? Plus 1. Oh, a little bit bigger. It's still huge, right? Infinity over infinity. So we have something that's getting big divided by something that gets big. So now I'm going to do the same approach. I'm going to look at the denominator. I'm going to look at the highest power of x that I see. The highest power of x that I see here is x squared. And I'm going to try and make that turn into just a constant. So I'm going to try and kill off x squared by dividing through by x squared, or multiplying through on top and bottom by 1 over x squared. So that'll be my next line. Limit x approaches infinity. All right, I'm going to come through out front with a 1 over x squared over 1 over x squared. And that will multiply through my 3x minus 5 over x squared plus 3x plus 1. And I will have to distribute that through, so I'll put those in parentheses. All right, let's try this again. Here to here. So let me rewrite the limit. Okay, what's 1 over x squared times 3x? So just see it, 3x on top of x squared. One of the x's cancels. 3 over x. Okay, and then next one, minus 5 over x squared, right? All over 1 plus 3 over x plus 1 over x squared. Everyone see that? Now, because we were careful about how we chose this, I promise you that on the denominator, you're going to just get a number. And let's see it. As we let x go to infinity, that goes to 0. Everyone clear on why that goes 0? Fixed over infinity goes to 0. Here, fixed over infinity squared goes to 0. Hey, what about the numerator? That goes to 0, doesn't it? That goes to 0. So initially you'd be like, oh shit, this is not going to work, right? We're going to get like 0 over 0 now. No, that's not what you get. What do you get? 0 over 1. And 0 over 1 is 0. That's not a problem, is it? It's okay to have 0 on top and a fixed non-zero number on the bottom. So your answer is 0. Was there a question? That looks like a question.
If the power on the bottom is bigger than the power on the top, is it always good?
It's always 0. You learn that in algebra. In college algebra, you learn that. You say, hey, look, if you have a rational function, right, and the power here is smaller than the power here, then your horizontal asymptote is the x-axis, or y equals 0. That's taught in college algebra. It's probably been a long time, but do y'all remember that there was like 3 cases, right? The powers are either the same, or the power on top smaller than the bottom, or the power on the bottom is bigger than the top, whatever. No. You know what I'm saying? Yes? So you're in college algebra, you're taught like, okay, yeah, just learn these 3 different cases and you're done. And that's great for rational functions. They have to be rational functions. I haven't given you something that's not a rational function yet, intentionally, because I'm trying to build up to it. So as great as that is, it's not always going to be able to help us, all right? I'm more concerned about this technique in that you can demonstrate you know what to do. You see infinity over infinity, you start thinking, how do I make the bottom turn into a number at the end? That's what I want you to start thinking. How do you algebraically make that happen? Any other questions? Doing all right?
So we're always looking to turn the bottom into a number?
At the very end, you want the bottom to turn into a number, which means that you need to take the highest power and think about how you can make that highest power cancel out. So here I put a 1 over x squared to make that cancel, right? We'll do one more easy, not easy one, we'll do one more friendly one before we do one that's a little more complicated. How about this? Limit x goes to infinity, x cubed plus 1 over 2 plus x, yeah, plus 3x squared. Well, where's the top headed? Infinity, okay. Where's the bottom headed? Infinity, right? 2 plus infinity plus 3 times infinity squared, that's a huge number, right? Infinity over infinity. All right, so I look at the denominator, I look for the highest power of x, and I try and kill it off. So where's my highest power of x? What is it? X squared, right? So it's not about the order of things, it's you're looking for the highest power of x. There it is, x squared. You want to try and kill this guy off, right? Just kill off the x squared. You don't need to kill the 3. Just the x squared's fine. So what should I multiply top and bottom by? 1 over x squared, right? So limit x goes to infinity. Here I come with the 1 over x squared over 1 over x squared. I distribute that through to x cubed plus 1. And then over here, 2 plus x plus 3x squared. Distribute through. I'm just going to write them down because of time. X plus 1 over x squared over 2 over x squared plus 1 over x plus 3. So that, does everyone agree with that? Look at it. Everyone see that? Yep. Which terms go to 0? Which pieces go to 0 when I take this limit? 1 over x squared and 2 over x squared and 1 over x. All of those go to 0, right? But there's some stuff that didn't go away, right? What didn't go away? X. Where does that go? Infinity, right? Infinity. So what we have here is infinity over, what's the bottom? 3. What do you think that is? We haven't really seen this before. What? I heard. Infinity. Think about it. You have a number that's getting big, divided by 3. Isn't that still a huge number? So here, the answer is infinity. Yes?
So, like to cancel out the highest power, we wouldn't go after the bottom, not the top?
Always after the bottom. Always. Yep. Because if you go after the bottom, you're guaranteed that when you're done doing the limit, you're guaranteed to have a number down here. Not 0. It'll be a nice number. It'll be either 1 or 3 or some other number, but it won't cause a problem. You won't have division by 0 or anything crazy. Yes?
So, the 1 over x squared is 0 because x squared is not.
Yeah, because think 1 over x squared, 1 is fixed, right? 1 is fixed. And then you're dividing that by a number that gets huge. That should get small. Yeah, because we're letting x go to infinity. That goes to 0. Yes?
So any fixed number in like the numerator divided by x would be 0?
Yes. Well, as long as you're taking the limit as x goes to infinity. Yes.
So what if the number was like negative in the numerator?
It would still go to 0. Because it would be going, they would be negative numbers, but they'd be getting smaller and smaller and smaller, getting closer to 0. And 0 is not positive or negative, right? Like 0 is 0.
Yeah.
So it's still approaching 0, it's just approaching through negative numbers instead of positive. But the answer is still 0. This all good? All right, let's see one that's not so good. That's a little, it's not that's going to be like crazy harder. It's just there's another layer that I'm going to add to this, a layer of complexity to it. So before I do the problem, I want you to think about something. All right, before I actually get into it, I want us to go back to some notation that we're familiar with and make sure we understand how this works. If I said take the square root of 27. You learn in college algebra class that you can rewrite this as the square root of 9 times 3, right? And then you're allowed to split that up into 2 roots, aren't you? Like you could split this up into the square root of 9 times the square root of 3. And then the square root of 9 is 3, right? And you get 3 times the square root of 3. That's how in college algebra you can simplify a radical. That look familiar to you? Everyone, yes? Here's another way you could have looked at this. This is also 3 squared times 3, right? 3 squared is 9 times 3, right? So that's the same thing as this. And anytime you see a pair of numbers being multiplied, like 3 squared, you can pull that out of the root as a 3 and get rid of it here. So it becomes 3 on the outside, root 3. I'll give you another example underneath that so that we're clear on that. If you see the square root of x cubed, let's not use 3 anymore. Another way you could look at that is being the square root of x squared times x. And because you have an x squared, you can pull 1x out of the root. Any questions? We're good? All right. So if you see an x squared in a root, it can come out as an x on the outside of the root, right? That's one kind of way you can see that. I want you to look at it backwards, the other way around. I want you to look at it this way. If you have an x on the outside of a root, right, and I ask you to push it inside, what are you going to do? You're going to square it, right? So if I tell you, hey, I don't like that root out there, I don't like that x out there, I want it under the root, you push it under the root, but then it gets squared on its way in. Yeah? Similarly, let's do something different. What if you had x and then here you had the cube root of x, not square root, cube root. And I ask you to push that x in. What happens when you push it in? It gets cubed. So this would become the cube root of x cubed times x, which would be the cube root of x to the 4th power. You see how I did that? If an x lives on the outside of a cube root and I tell you to push it inside, it gets cubed when you put it in. And then you can multiply them together and get x to the 4th. Over here, if I want you to push this in, you push this in, it becomes x squared times x, which becomes x square root of x cubed. Okay, we good? All right, let's do a problem now. Let's do the limit problem now. Put a star here, because most of the time, this is the type of problem that would appear on a test. Limit x goes to infinity, 6x minus 1 over the square root of 4x squared plus x plus 1. So here's the deal. those rules you learn in algebra about, looking at the powers and if the power on top is bigger than the bottom, all that works if you have a polynomial divided by a polynomial. We no longer have a rational function, so we don't have a polynomial divided by a polynomial. The denominator is a square root function. It's actually a very complicated square root function because underneath it is a quadratic function, so it's just a mess. But we still want to see what's happening, right, and see how we handle it. So let's just let x go to infinity first. And when we do that, the top heads where? Infinity, and the bottom heads to, let's take our time through it. 4 times infinity squared, that's infinity plus 1. Everything under the root is getting infinitely big, right? What happens when you take the square root of a number? It gets smaller, right? But it's getting bigger and bigger and bigger. So you square root it, yes, it'll make it smaller, but it keeps growing. So it's just going to keep getting bigger and bigger and bigger. The square root really doesn't have that big of an effect on it. Does that make sense to you? So it still grows without bound. It still becomes infinitely large on the bottom. So what's the rule of thumb when we have infinity over infinity? Look at the denominator, find the highest power of x, and kill it off. So the highest power of x you see here is what? X squared, right? So I need to kill it off. Now normally I would come in here with 1 over x squared over 1 over x squared, right? I would do that. But the problem is that I've got to come in with a 1 out here. My 1 has to be out here, so I do it top and bottom like this. So whatever I put here is going to live outside of this root. And then I'm going to have to push it in. And so what I want is to put something out here so that when I push it in, it will kill off the x squared. So whatever I put out here, it gets pushed in and gets squared and then kills that off. So what should I put out here? Yes, not x. I don't put x here and x here, because if I put x here, it goes in, becomes x squared, and then multiplies through, doesn't cancel. 1 over x. That's what, whoever said that, I think that's what you meant, but it's 1 over x over 1 over x is what I'm going to put on the outside. The main thing is that you understand why I'm using 1 over x and not 1 over x squared. So let me do it. I'm going to put 1 over x on the top, 1 over x on the bottom, and then 6x minus 1, and then over square root of 4x squared plus x plus 1. I should tell you that if you go to a tutor or something about a problem like this, they may do something a little bit different. I'm just like warning you. This is the way I teach it, so it's the way I teach it. Does anyone have a question on why I chose 1 over x? Everyone understands that when I push this in here, that gets squared, right? And when you square that, it becomes 1 over x squared, which is what I need to kill off x squared, right? So let's do on the next line, let's push it through. Now on the top, it's nice, it just goes through, right? It doesn't square, right? The top doesn't square because there's no square root. So it just distributes through. Limit, x goes to infinity. Okay, I have 6. 6 what? Minus 1 over x. That's my top, right? On the bottom, I'm going to take a little bit more time on the bottom. On the bottom, I push that 1 over x in. When I push that in, it becomes a 1 over x squared, but I still have to distribute that through to what's there, right? That has to go through to all 3 terms. So when this goes in, it gets squared on its way in. And then next line, limit, x goes to infinity. Okay, 6 minus 1 over x over, all right, we still have a square root. Don't make the square root disappear, it's still there. All right, what do I have under that root? What's under there? 4, right? That's when you multiply here to here, the x squareds cancel, you should get 4 plus 1 over x plus 1 over x squared. All right, you see it? Now, let's just let x go to infinity. Anything that has a number over x should go to 0. So that's going to go to 0. That's going to go to 0. That's going to go to 0. And so what's left up top? 6. And on the bottom? Square root of 4, but the square root of 4 is 2, so your answer is 3.
So for the, when there's this a group, do you always go one less than the problem in it, or?
No, because if that was a cube root, we might do something different. Yeah, you have to investigate each problem. There's not like always do
So
this.
if it was cube, would you do 1 over x squared?
Well, you mean if this problem was cubed or cubed in general?
What if
Do you want to look at this problem with the cube root?
Yes.
Okay, y'all want to try that? Okay, that's a harder problem, but we'll do it. So let's just do the same problem with the cube root. I can't give you like a general answer. Like if you ever see cube root, do this, because what matters also is what's inside. So let's see what happens here. All right. So if we change the problem slightly and we make this a cube root instead, do we still get infinity over infinity? We should, right? The cube root will make that smaller than the square root was, but it still keeps growing and growing and growing. So it should become infinite. All right. So you've got to kill off x squared, right? But whatever goes in there is going to get cubed on its way in, right? You agreed? Whatever's out here, when it goes in here, it's going to get cubed on its way in. So this starts to get tricky, like how do you do that? So let me show it. Let me show it, and then after I show it, I'll explain why. Okay, let me write the original problem here. Okay, so I'm trying to figure out what am I going to come in with out here. It's going to be 1 over something, right? 1 over something. The reason I have to do a fraction is because, remember, we want to kill off the x squared, right? We want it to go away. So I want to make sure it's on the bottom. So at the end of the day, I want an x squared to go under that, right? X squared on the bottom. But I know it's going to get cubed on its way in. So just watch what I do. I'm going to do x squared, which is what I want, right? That's what I want. But then I'm going to take the cube root of that. Why? What would happen if I take the cube root and cube it? It cancels out, right? So when I push this in, the cube root's going to go away. Make sense? On the previous problem, what did we have down there? We had this, right?